Number 5. Automobile traveling in a straight level road. Alright. Initial speed v, brakes are applied, comes to rest. Got it. It travels a distance x to do it. How far would the automobile travel in coming to rest if it had the same acceleration, but an initial speed of double? Okay. You should kind of, you get kinetic energy probably involved here, and they're doubling the, yeah, right? Okay, so it ain't gonna be double. I promise you that right now. So let's just do this. What's the kinetic energy in the first situation? Would just be 1/2 the mass of the car, the original velocity squared. Right? Because it's just m we'll call m for the car, and they say it's just v, so we'll use v. No big deal. What about the kinetic energy in the second situation? Well, that would be 1/2 same car, so mass, times its velocity would be 2v squared, which would mean it would be 4. We looked at this in an earlier problem, times 1/2 times m times v squared. It would be 4 times the original kinetic energy. This 2 would get squared to be a 4, and I'm just going to write it all the way to the left, put parentheses around it, just to highlight the fact that, remember, this is just the original kinetic energy the first time around. So really what you have is 4 times, so the kinetic energy in the second situation is 4 times the kinetic energy in the first. And at first, well, right now you're probably like, oh, that's great, Wellborn, but they didn't ask us about the kinetic energies. They asked us about the stopping distance, bro. To which I would respond this. Work energy theorem says that change in kinetic energy is equal to the net work done. Now, this is important. So whatever the kinetic energy it had in the beginning, it loses all of it. In both cases, it comes to rest. So each of these are the change in kinetic energy. If you have $100 and you lose $100, your change is $100, right? So, and we could put negatives in, but blah, 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 blah. Well, I guess we should, I guess. But point being is the changing, we have those. One of them is KE, and the other is 4 times that KE. K2 is. What about the work done? Well, what's the force stopping them? Well, in this case, it'd be friction. It doesn't really matter because it has the same acceleration. It must have the same net force. So it's whatever that net force is, caused by the brakes, it's friction probably, times the stopping distance. So let's use D right now. So the work energy theorem is how we're going to get the distance. For case 1, you have just KE is the, we'll call it negative if you like, is the change in kinetic energy equals whatever that net force is times the stopping distance they give us is x. All right, so no big deal. I guess I'll write x equals, technically this force would be negative as well, so the negatives are going to cancel out, would be KE over the net force. Let's see if that helps. Now, in the second case, I have 4 times the kinetic energy that I lose. Same net force. I want to know how big is x in case 2. Well, let's do this. Let's divide by the net force. So I have 4, well, let's do it this way. x2 equals 4 times KE over net force. And I wrote it like this on purpose. I divided both sides by net force. That's why it's in the bottom. And KE's up in the top. And I deliberately wrote the 4 off to the side. Why? Because this right here is just that. It's x. So the stopping distance in case 2 is 4 times the stopping distance. Because the force can't account for it, can't push any harder or slow it down any better, the extra energy has to be removed by the extra distance, and there's 4 times the energy when you double the speed. So if you triple your speed from 15 miles an hour to 45, you're probably thinking, no big deal, 45 isn't fast. Whatever distance it would have taken you to stop, at 15, it's not going to take you 3 times more. It's going to take you 9 times the distance to stop. And in a development, little kids running around, it'd be kind of important to note that. So it's something they usually point out in driver's ed, and it's something that I feel pretty strongly about. Slow the hell down. There you go. So I'm looking at 4x for that one. I won't preach at you too much, but you know, you don't want that to happen. All right. Number 6. All right, 15 of them. All right. Pardon the ridiculously dark line from the copier. We'll live with it. So, a cart is constrained to move along a straight line. A varying net force, so this is time, and this is velocity. Interesting. There's a changing force on it. That's why I guess they have different shapes, should be. Along the direction of motion is exerted on the cart. That would mean with it and against it, though, I believe. The cart's velocity v is a function of time as shown in the graph. During some part of the motion, the work done on the cart is negative. What feature of the motion indicates this? Okay. This is really, once again, a lot of them are going to be the work energy theorem. Change in kinetic energy is equal to the net work done. So, the net work is going to be negative when the change in kinetic energy is negative. That means slowing down, right? It doesn't matter what direction you're going because kinetic energy is not a vector. So if you slow down, your kinetic energy decreases. That is a negative change. So what I want you to look at here is on our graph, which of these segments shows the thing slowing down? Remember, this is 0, and it don't get any slower than 0. So A to B, speeding up. It was going 0 and it ended up going 8. That's speeding up. Here it doesn't change its speed at all. That isn't slowing down. Here we're slowing down, aren't we? We go from 8 meters per second down to 0. That would be the definition of slowing down. This, you think, oh, it's going down too. No, this is speeding up, isn't it? Because you're going negative 4 meters per second, and you're like, but it's negative. It's no, we ain't in math class. That's just a car in reverse. I don't want to get hit by it. I don't want to get run over by something going in reverse anymore. I want to get run over by something going forward. So this is speeding up. As far as kinetic energy is concerned, you're just going faster. Doesn't care. So it would be important to note at this point. So this is not what the question asks, but I just want to point it out. That if you had a segment in here that went from, say, here to there, that would be something slowing down. It had a negative velocity, but it slowed to 0. So this would be a negative change in kinetic energy as well. But for us, the one in question here is right there. That's slowing down. That's a negative change in kinetic energy, which must mean, so what feature of the motion indicates this? Speed is decreasing. So it's going to be CD. So for which segment does the cart move the greatest distance? Ooh, this is going all the way back to, so this is number 7, by the way. I should put that up here real quick. No. We'll wait for a second. Alright, so number 7 says for Which segment of here does the cart move the greatest distance? This is actually a throwback question. You're supposed to know that in a velocity versus time graph, the displacement slash distance is the area under. So we look at our graph, and for each segment, I'm going to go nuts with the highlighters. We find we consider the area under. So like AB, that would be this. I failed coloring in kindergarten. For DE, it would be this. We'll do CD would be this. And we'll just leave the area under BC to be white. So which of those has the biggest area? Let's count the blocks. Area under BC is 1, 2, 3, 4, 5, 6, 7, 8. Okay, that was the easiest one. The green one, well, that's going to be a triangle. So it's half of, but it's the same dimensions overall, so it'll be half of that. So what was this? 1, 2, 3, 4, 5, 6, 7, 8. This is going to be 4. This is 8. This guy, well, 1, 2, 3, 4, 5, 6. I believe you could say that, for example, this piece here probably matches up fairly well with, say, one of these two. So you could estimate a little bit. 1, 2, 3, 4, 5, 6. This is 7. I'm guessing that this and this would make 8. I'm thinking this is more than 8. So I would think this is greater than 8. Certainly this isn't. And by the way, the fact that it's negative, while it would mean something for displacement, for distance traveled, it would just be whatever the number is. So this would be actually 1, 2, 3 times 2. That's 6. Cut in half. That's 3. So I'm going to go with the pink AB is the biggest area. But that's a throwback question. That's not a that's not an energy question, really. So yeah, I would go with that one. All right, 8. I think 8's going to use the same graph, right? Oh no, it's a different question, different topic. I'm eating pretzels. I'm sorry. I gotta eat. Been screencasting all day. Alright. 8. Which of the following situations is the kinetic energy of the object decreasing? So, slowing down, right? That's all you want to think about. It's really, they're saying, which of these, you could ask a third grader this question, I bet. Alright? So let's say, sphere is dropped from a building. Ooh, they want to get you with that one, right? Because it's going down. You want to think, ooh, that. But the sphere, why can't we just call it a blind way? That's speeding up. So that's not a decrease in kinetic energy. Kinetic energy is increasing. The satellite is moving in a circular orbit around Earth. No, not. We're assuming uniform circular orbit would be uniform circular motion. So it's never speeding up there. It just stays at constant speed. So no. Baseball is heading upward after being thrown at an angle. Ooh. So, as the ball goes up, it has a certain amount of velocity here. The velocity here is only the horizontal component. It is going slower here than it was at the start. In fact, because the y component is being reduced by gravity, it's going slower and slower on the way up and faster on the way down. So I like this one. Baseball heading upward, that should be slowing down. An elevator is moving upward at constant velocity. Constant velocity is not slowing down, so it's got to be C. All right, number 9. Cart is moving on a level track in the positive direction. Hence the, we don't know, okay. A force acting parallel to that axis is exerted on the cart. The graph above shows the net force exerted on the cart as a function of displacement. All right. As the cart, what is the net? Okay, so here is, I don't think we've run across this fact yet, and it's an important one. Here's the fact that you need to know for this. And there's going to be other questions that this is going to come up in, I'm sure. In a force versus displacement graph, or distance graph, displacement works. The area under the curve is the work done. And in this case, if it's the net force, it's the net work done. It might be, if it's just a single force, it may not be the net work done, but in this case they specifically say the graph shows net force exerted on the cart. So this is net force versus, it means this is the net work being done, is the area under. Okay, so area under this, well, that's 2 times 10, that's 20. And that would be joules. Force times distance. This, so remember, it was moving in the positive x direction, and then they put a negative force on it. That's going to slow it down, isn't it? Which would be negative work, right? So it makes sense that this will be negative. So this is negative 5 times 2, that's negative 10. So what is the net change in the kinetic energy of the cart? So this added 20 joules into it, increased the kinetic energy. Remember, net work is equal to the change in kinetic energy. So this changed the kinetic energy by bumping it up by 20. This lowered it by 10, so the net change should be up by 10. I'm going to go with B on that one. All right, on to number 10. Force F is exerted on a 5 kilogram block to move it across a rough surface. Rough surface, friction. As shown above. What I'm supposed to tell it's rough. Anyway, the magnitude of the force is initially 5 newtons, and the block moves at a constant velocity. All right, keep that in mind. While the block is moving, the force is instantaneously increased to 12 newtons. How much kinetic energy does the block now gain as it moves a distance of 2 meters? Okay. So really, what we're saying, the first part of this, when they say that initially you pull it with a force of 5 newtons and it moves at constant velocity, well, that means there must be a 5 Newton force going the other way, right? That's friction. This is your applied force. And this is all right in here. The force is initially 5 newtons and the block moves at a constant velocity. So those two forces are equal. Of course, weight, normal force, they'll cancel out as well. Great. All that is doing is letting you know that friction is a force of 5 newtons. Because friction doesn't care how hard you pull, it can only do what it can do. And it's based on the normal force and the materials, and we're not changing those. So this is just a fancy way of saying, hey, the force of friction is 5 newtons. To the left, we'll say. Then they apply a 12 Newton force. Make it larger. And of course, weight, normal force, blah, blah, blah. But what's the net force on this thing? Well, if friction's 5 and that's 12, then the net force is 7 newtons, correct? All right. And you're like, well, they're asking us about kinetic energy. Oh, come on now. Come on now. You know that net work is equal to the change in kinetic energy. So in an earlier problem, one with the graphs, and one we just did recently, we looked at this one and we found that this was the net work done by one force, and then later on they put a different force, and that was a new network, and we combined the two works to get the net work. Well, another way to get net work is to just use net force. So another way to look at net work is the net force on an object times the distance that net force x is equal to change in kinetic energy. So 2 meters. The net force I figured out now is 7, because they gave me enough information to realize that the friction must be 5. And then I got 7 newtons times 2 meters equals a change in kinetic energy, so it should be 14 joules added on. Number 11.